Okay, so for the convolution mixer, the only breakthrough is right here, okay, as I just mentioned. We go for a P by P patch, or you can consider patch as a filter with a stride of P, okay? And then you do the convolution. After that, you just go just like any CNN architecture, okay? But for in the paper here, you apply the depth-wise convolution and then for pixel-wise convolution, okay? So you can speed up the calculation, and it require you will reduce the memory for the parameter storage, okay? So that's it, okay? So here, just give it the procedure, okay? BM batch normalization, okay? The stride is P. The kernel size or the patch size is P by P, okay? And then you go for the depth-wise convolution and then point-wise convolution, okay? So, and also you use a Gaussian arrow, okay? Activation function, okay? So that's it, okay? And after page 52, I show you another implementation code, okay, for MLP, okay, and the test data set is handwritten digits, okay, 0, 1, 2, and up to 9, okay, just like this, okay, and you show the model, okay, and the details of the model. We just use a fully connected layer, okay, the dropout, the percentage, okay, is 25%, okay? And here is the automation. So if you have some question, you can just take this as an example. And here is Keras code, okay? How to load the data set, how to, and here you just use the dense layer, right, with some of the parameter and the activation function. You use a rerun. Then you can check for the Keras to look for more variable or other alternative for the activation function. Okay, and also you will print out the details model architecture. Okay, it will show you what will be the output size after each layers. Okay. And the number of parameters used for each layer, okay? Okay, so you can go through the detail if you want. And this example here is just show you how to use the deep learning for alignment or so-called positioning, okay? This is the PCB. So the first thing, no matter for inspection or for assembly, you need to find the position, okay? You need to align, okay, the position of the PCB. So, so this is a regression problem. This is a regression. 它是回归问题啊，这是一个回归问题。You need to estimate what is the shift in the x-axis, y-axis, and what is the rotation angle for that, okay? So it's a regression model. So you can take a look, okay, by using MLP, okay? So you take each pixel as an input node, okay? But actually this problem it will be better described by the CNN model, okay? So the following example or the code will show you how to do it, okay? So just for your reference, okay? Again, then we'll see how to use the CNN, okay, for classification. Again, handwritten digit. Okay, here's the architecture. For this one, you just go for 1, 2. Okay, just 2 convolution layer. Okay, and followed by the maximum pooling. Okay, the size you use default. Okay, that's it. Okay. Use a quite small learning rate 0.001. Okay, that's the. If you have no idea, you can just starting from here. Okay. Okay, and here's the code. Okay. Here's the code. You can see convolution to D. Okay, if you do the convolution with the time series data, then will be convolution 1D, okay? So here you need to specify what should be the filter, okay? The number of filters, the kernel size, for this case, 5 by 5, okay? The same is going to maintain the original size, okay? So you need to input something like this and also the activation function, okay? And go for the max pooling. Then dense layer. Okay, as I mentioned, you have a better use to drop off at the dense layer, not in the convolution layer. Okay, that will be the better practice. Okay, so if you have a question, and this is a CN for regression. Okay, to estimate the position. Okay. Of PCB, okay. So again, the basic model is the same as the previous one, but the output, I should see. Let's just see the output. It's only 3, okay, which will be what? The translation in x-axis, translation in y-axis, and the location, okay? So why the last output layer has a 3 node, okay? You use a 3 node, and they are all fully connected, okay? Fully connected. That's the idea. And remember, because we are talking about the regression. Okay, so the final activation function you use you use linear. It does not use relu to prevent you will suppress the negative value to be 0. Okay, because the rotation could be a positive 10 degrees or minus 10 degrees, right? Okay, that could be possible. So you use linear. Okay, it does not apply any, and actually. It means it just simply just take the output, okay, from the previous layer, okay, for the last layer, okay, for the output layer, let's say, okay, and then you can read the details, okay. So that's all about convolutional neural network, okay. And any question before we go for the next topic? Okay. CNN basically is used for supervised learning. Okay, when I say supervised learning, which means you need to do the labeling or annotation. Okay, you need to input. You need to provide the input and the corresponding output manually. Okay, so our next topic. Okay, before I go next topic, any question? I need to clarify. Okay, if no, here's depth-wise. Okay, after you have learned this, okay, I already mentioned, okay, it separates the depths, okay, into individual channel, okay, and after that, we go for the point-wise convolution, okay. Before that, you need to concatenate the result together, okay? Okay, so for this case here, original imagery is is 7 by 7, the depth is 3, so that we need 3. We need 3, 3 by 3, by 1, okay, by 1, okay? And after that, because it will reduce, right, the outer boundary, so the size will become 5 by 5, but the depth will be 33 because we go for the concatenation. But after that, suppose we want to change the channel from 3 to 128, but if for this case, the size is only 3, okay, 1 by 1 by 3, so we only have a 3 parameter, so 3 times 128, so it's quite small, right? It's quite small. It's only about 400 something, okay? Compare the original, if you go for 3 by 3 by 3 and by 128, then the number parameter will be 3,000, more than 3,000, okay? That's the, oh, okay, it's right here, something, okay? If you go for the original way, you need the number, just for this convolution, you need 3 up to 300, 400, 3,400 something parameter. But if you go for the depth-wise separable convolution, you need only 411, okay, parameter. You can reduce the number of parameters a lot. But remember, the result won't be the same, okay? The result won't be the same. You need to verify will be okay if you go for the depth-wise separable convolution, okay? Okay, so that's the supplementary material to explain this information. Okay, our next topic will be autoencoders. Okay, autoencoder, as I mentioned here, basically is used for supervised learning, which means you need to provide the label or notation. Now, when we comes to the autoencoder, it means it's used for unsupervised learning. Okay, used for unsupervised learning. 也说它是会监督式的学习啊。It means you need only have to collect the data. You don't need to do any manual notation, okay, or labeling. This is preferred especially for the industrial guy, okay, for the user, because they don't need to do anything. The only thing they have to do is just to collect the data. That's it. Okay, just collect the data. And why is unsupervised? For any autoencoder, it has the form. Okay, the form like this. The first part called encoder. The second part called decoder. It must have this form. Okay, called autoencoder. Why called auto? Nothing to do with automation. Okay, nothing to do with automation. 跟自动化一点都没关系。Auto means autonomous. 也就是自我。Why call auto? That's because the output is the same as the input. Let's say, okay? That's why I call auto encoder. Auto 叫自我回归 ，OK？ 啊，或是自我编码，它是自我。不是自动化，跟自动化一点关系都没有 ，nothing to do with automation. Okay, just like auto regression, you have heard this, right? Auto regression, right? Something like that. Okay, you do the regression, but based on the same signal. Okay, in different part of the same thing. It's called autoencoder, okay? Because the output, when you train the model, the output will be the same as the input. That's why you don't need to do the train. You don't need to do the labeling. You don't need to do the annotation at all, okay? That's most preferable model for the user, right? The only thing they need to do is just to collect the data, okay? What is encoder? The purpose for encoder is for feature extraction. Okay, or it played the role as a feature extractor. Okay, especially for the unstructured data, such as time series data, or image, or video. Okay, you don't need to provide the feature. You leave the work to the encoder. 啊，这个叫编码器，编码，也就是说呢，把很复杂的资料呢变成一个简单的。Okay, so we find that the other purpose for the encoder is we try to reduce the dimension, we try to reduce the complexity of the information. Once you have the extracted the features, then we come to the decoder. Okay, 这是编码器，这是解码器啊，这是编码。Okay, 解码。The purpose for that is, suppose X is the image, then it will be the image generator. Okay, it's a generator to generate an image based on what? Based on the feature. Okay, based on the feature. Not based on X, but based on the feature. Now, the objective is simple. Suppose this is output, okay? Now, the loss function can be simply given by, try to minimize. Input. And the output. Okay, we try to minimize. If we go for the mean square error, okay, we let I means sample I, okay, sample I. We let the input, we let the output, the estimated output the same as the input, okay. Now it will run what? Run the most representative features, okay. And hopefully we can reconstruct it, the input, okay, the same as the output. We try to minimize the reconstruction error, okay, this so-called reconstruction error, okay. Try to minimize the reconstruction. Error. Okay, that's the whole idea, okay, of the autoencoder. Actually, we have done this, okay, but that's the, and this model used a lot in a image generator, okay, no matter user, and the encoder decoder can be a CNN, it can be a transformer, or it can be a LSTM. Okay, sequence to sequence model. It can be any model, but most of the cases we simply use a CNN model. But it can be a transformer. Okay, 编码器、解码器可以是convolution neural network， 它也可以是 transformer， 它也可以是像 time series 的那种 LSTM 的模型，都可以。不过它一定要 you need a pair of encoder and decoder. Okay. Okay, now we can go back to the autoencoder. Okay, autoencoder. I will introduce the most typical or commonly used autoencoder. The very first one, convolutional autoencoder called CAE. The other one, another very famous one called variational autoencoder called VAE. Okay, CAVE. I will introduce what are the difference between these two, and what does it mean by variational? It's based on the statistical some techniques. Okay, so let's go for the convolutional autoencoder first. Okay, the name implies we simply use CNN. Okay, well actually it can be replaced by the transformer. Okay. Actually, the traditional VAE still use a CNN model, but the objective is quite different. The objective, the loss function are quite different. Okay. Okay. Anyway, it's for unsupervised learning. Okay, for unsupervised learning. So one of the purposes is try to extract the features. You are trying to extract the representative features， 就是它自动去攫取你要的特征。Okay， 你不用去设计，你不用去烦恼You don't need to worry about how to design the feature. Okay, manually. Okay, with some of the experts' knowledge. Instead, we let the autoencoder to extract or to design the best representative features. Okay, based on what? Based on the input. Just based on the input. You do not have to provide any further information to tell how to learn the model. Okay. Okay, so anyway, the purpose for autoencoder, I already mentioned that can help you to extract the representative feature. It can be used to denote, okay, to design. 就是你一张影像里面有很多杂讯，你可以透过这个自我编码的方式呢去杂讯。Okay, denoise. Actually, there's a model called denoise CAE. Okay, but for industrial application, I don't recommend it to use denoise CAE. Okay, I will explain why. Okay, the better way will go for the VAE for denoise. Okay, will be better than CAE. Okay. Because the preparation of the input data could be different for CAE and VAE, okay, especially for denoise application. And also it can be used for image reconstruction. If you can use it for image reconstruction, you can use it for image generation, okay, to generate new image. You can generate image by changing what? By changing the features, okay, purposely, okay. Okay? So here, this is an MLP model, okay? We just have the fully connected layer. We input X, and the output is also the same as X, okay? I keep saying, that's why it's unsupervised. You don't need to provide any further information about X. Right? You don't need to label, or you need to assign the class or anything. Okay. Now the whole idea here is we do the compression. Okay. We do the compression to compress the input, the complicated or high dimension X into a low dimension features. Okay. Usually we call it Z. Z can be a what? Representative or so-called latent variable, okay? Latent variable, 隐藏式的变数. Okay, Z is learned by the model, by the encoder, okay? And you need to learn a good representative feature Z so that the decoder can reconstruct the input X, okay? So that the output will be hopefully will be exactly the same as the input. If you have good training about the latent or representative features, Z. Okay, that's the idea. Okay, so either you can go for the MLP or transformer, but we will introduce a lot about how to use CNN to do the job. Okay, encoder, decoder. Okay. Okay, so anyway, here is our simple loss function. Okay, that's the input. X prime will be our output. Okay, I put FG here. F means the encoder. Okay, network. G will be the decoder network. Okay, so we try to learn the encoder parameter and decoder parameter so that we will minimize the loss function, which means we will minimize the reconstruction error. Okay. but it does not have to be a mean square error. Sometimes you can use cross correlation. Okay, if we specify the input x, the value between 0 and 1. Okay, sometimes you can simply just use cross correlation. Okay, so I will skip some of, for MLP, what you need to run is the fully connected weight, okay, which is the encoder weight, okay. If we have only an input, here's the hidden layer. For this case, we use up to 4 dimensions. We use 4 nodes, which means we are convert the input into a feature vector with the dimension of 4. Okay, let's say. And then you need to run the decoder weight. Okay, D means decoder weight is fully connected for the output. And hopefully the output, okay, the output in the node will exactly the same as the input, okay, of the node. Right, that's the only, okay, this is a simple way, as we know. When because it can only represent the linear combination, right? You can only find linear combination, so usually you will use more than one layer. You can use 1 hidden layer, 2 hidden layer, or 3 hidden layer. Okay. Of course, the number of layers does not have to be the same. Okay, for the encoder and decoder, they can be different. But usually, most of the time, we will use the same number of the hidden layer for the input and for the output. 就是说这边你要用几个 hidden layers。给 encoder 还有几个 hidden layer 给 decoder， 事实上可以不一样的哈。可是没有特别的目的的话，基本上我们会用一样啊，除非你为了节省时间啊，或者是什么什么，有时候会用不一样。OK， 不然的话我们都会用一样。OK，so let's say OK，so that's the basic idea. Now here we comes the CNN. Okay, again, it's an encoder, decoder. Both are the convolutional neural network. 都是 CNN 模型，好吧？跟你前面谈的。So it can be what? It can be VGG. It can be VGG. It can be residual net. Okay? It can be transformer. Or it can be any neural network. Okay? But the purpose, whenever we talk about, say it's an encoder, is try to find the compressed representation, which means we try to find the representative features. Now, how many features we need is given by the user. Okay, you need to determine. Now, if you give only, for example, just give 1 or 2 features, you know the reconstruction error will be very large because you cannot just use a couple of representative features to recover the whole input, right? So, of course, if the number of features here is the same as the input, then it serves no purpose for the encoder, right? So usually, we will compress the original high dimension signal into a low dimensional representation, okay? But how many will be enough depends on what will be your required image quality. Okay, image quality. 你要重建的品质，你到底关不关心 ？Should be very fine. You want to recover all the fine detail, or you don't care about the fine detail. You just want approximation of the image, then you can use less dimension. Okay, for the representation. But if you want to recover all the details, then the number of features could be very large. Okay, so it's all up to you and up to the user. You need to determine what should be the size for the feature vector. OK， 就你的向量，这是你要决定的，没有人可以帮你决定。OK， 那越多呢，还原就会越好，还原就会越好。越少的话呢，大概你只能得到它比较平滑的，或是它的大略的表征而已。OK，so here's some further example. First, we make sure that the output will be the same as the input for the training. Okay, then here comes the convolution. Now it will involve the convolution, or the convolution plus the pooling. Okay, convolution pooling. And usually for the pooling, we use a standard 2x2 with a stride of 2. So after each convolution, the size will reduce by 2, by a factor of 2. Okay. For example, for the original size, it's 100 by 100. After that, the image size or the feature map size will become 50 by 50. Okay. It will reduce by 2. Okay. Now, after that, then you will go for the fully connected layer. Okay. Or you don't at all. That'll be fine. It does not have to be connected, which means you can use the feature map in the last layer of the encoder as the feature. That'll be fine. 也就是说哈，你不见得一定要用 fully connected layer， 你可以直接 you just have the convolution layer, okay? But the feature map in the last layer 在最后一层，你可以直接拿来当成是它的 feature vector, okay? But that's the usual way. We do the convolution and then we go for the fully connected, okay? And then we use this will represent our extracted feature, okay? That's right here. We use this as okay. If you go to fully connected, then you will connect to another fully connected for the decoder, and then we do what? Do the so-called deconvolution. Deconvolution. Deconvolution is nothing but another convolution. Okay, but we just make it the terminology a little bit different with respect to the convolution. But actually, it's not exactly the same as convolution. I will explain that later on. Okay. And plus up-pooling, because if you go down-pooling, we reduce the size. In decoder, you need to the up-pooling, which means you need to enlarge the image. You need to so that the output will have the same size as the input. Okay, because after each convolution, the size will getting, especially after the pooling, the size will getting smaller and smaller, right? Okay, but when we go to the deep convolution, the size, you need to enlarge the size. So usually, if the down size is a factor of 2, then in the decoder, we will upsampling also in a factor of 2. Okay, so if this is reduced to 50 by 50, and this will be 50 by 50, then we will upscale to 100 by 100, so that the final output layer, the size of final output layer will be the same as the input, okay? The input layer, okay? So that's the idea, okay? Let me say it again. For the standard CAE, you can use the fully connected, or you don't use it at all, okay? If you don't use the fully connected, you simply use the feature map in the final encoder layer, okay, or the final pooling layer as the features, okay? You simply use just the feature, that'll be fine, okay? Then it's all up to you. 所以我们最后再用，你可以不全连接成也没关系，可是呢，一般来讲，假如是这样，你会用它的最后一层啊，用它最后一层。的 feature map 当成是你的特征值 ，OK？ So that's it, okay? That's all you can do, okay? Okay, so that's the idea. As I mentioned here, okay, the loss function. If y is the output of your autoencoder, then you can use this the mean square or square arrow, okay, major reconstruction arrow, or if the output is what did I say here? If the output, okay, if the original input is between zero, is either 0 or 1, okay? Then, and the output could be a softmax, that will be a probability that will have the value between 0 and 1, right? Will be in the range between 0 and 1. In that case, you might use this, okay? The so-called cross entropy, okay? This is the cross entropy, okay? So X will be the input, YK will be the output, okay? SK. Because X can only be 1 or 0, that's another way we express it, okay? That will be another so-called cross entropy. And Y will be the softmax output, okay? We expect it to be 1 or 0, but sometimes it will be 0.8 or 0.3, okay? Anyway, that's another major. So what I try to say is it does not have to be mean square. It does not have to be mean square error, okay? It does not have to be mean square error. It can be only based on the entropy, okay? This is actually a binary cross entropy, okay? Okay? Okay, anything about CAE? It's quite simple, okay? The input, the output is the same as the input. For the user, you need to specify what should be the feature size, okay? The feature size, or the size of the feature, or the dimension of your feature vector, okay? Is up to you, okay? Now, here comes the variational autoencoder. You use a lot in a lot of up-to-date model, okay? Up-to-date model is still based on the variational. It's called variational, that's because it's based on the statistical so-called variational inference, okay? Variational, 这个叫变分嘛，变分，中文叫什么？哈 ，variational inference, okay? INFERENCE, okay? Variational inference. Okay, here's the idea. That's the idea. We still need encoder and decoder. And the encoder and decoder are nothing but, again, can be a CNN model. They are neural network model. But the idea is right here. What we call the variational network is, given the input X, that's the input X, okay? We want to estimate the probability, or we're trying to estimate a good probability of the latent, the so-called latent variable Z, which will be the representative features, okay, the Z, okay, and this is for encoder. So for encoder, it's try to learn the neural network. Given X, we try to maximize the probability that you can observe the representative feature Z. And because we know nothing about Z, so usually we simply set up Z will follow a manageable distribution. Okay, this is just for Z. This is a conditional probability. Given X, I want to know what should be the outcome for Z. Given that Z will follow some manageable probability. When I say manageable probability, what will be the good choice for that? If I have no idea at all. Anyone? Actually, there could be just only one you know. In statistics, what should be the probability? 一定是高斯嘛，而不是高斯来说。It got to be Gaussian, right? If you have no idea, it may not be Gaussian, but since you have no good idea, now we simply assume it is Gaussian, and we make it Gaussian, and it works. That's the idea. It works. Okay. So we simply assume the Z will follow Gaussian distribution. Now, given the Gaussian distribution, we try to find what will be the maximum likelihood for Z, given the observation of X. Then you can figure out the Z. Actually, for this variational autoencoder, the output for the encoder will be what? What do you know? Will be the mean and standard deviation. The mean and the standard deviation is learned from your input. The output will, let me say it again, the output of the encoder will be the mean and the standard deviation, which will represent each features. So the difference between CAE and VAE is what? For CAE, remember whenever we talk about the CAE, I don't need to repeat. Given this, we give X. Expect output should be also X. It will run the feature representation. So Z, given X, Z will be fixed. Will be fixed. Okay, once you run it, Z is fixed. But for VAE, when you run the autoencoder, the mean and standard deviation is based on the probability distribution, which means every time you run the VAE, you won't get exactly the same answer, even the input is the same. You know what I'm saying? They will be very similar, but they won't fix, not like CAE. Once you run it for a given input X, no matter how many times you run it, you will get the same answer, but not for VAE, because VAE, the representation, the latent variable is represented by the mean and standard deviation of the Gaussian distribution. Under the assumption, the latent variable will follow a Gaussian distribution and a standard Gaussian distribution. 也就是说，我们希望这个 Z 它的出现的几率呢，它的分布呢是标准的常态分布。When I say standard Gaussian distribution, I mean what? The mean, zero mean, with the unit variance. 标准差是1。对，我没有说它的范围介于0跟1哦。I didn't say that it's a limit between 0 and 1. I just say it has the mean of 0 with the standard deviation of 1. But the value could be infinite, large, or even negative. But the probability could be very small. That's it. Okay. Now, for the decoder, given Z, okay, given the latent variable, we try to find the probability. We try to maximize the probability that the output will be X. That's it. Okay. That's it. But no matter what, all the operation is based on the CNN or even transformer, that'll be fine. But the objective could be a little bit different, okay? And the output is not a fixed value, not like the CAE, okay? The Z is not fixed, but the Z will follow some distribution. Okay, so with this in mind, let me show you the example here. Okay, it needs a lot of mathematics, but let me just give you something here. Okay, this is a very good example. Okay, you can find more detail from by Google this information. Okay, now here we have an input. Okay, a man with beard is smiling. Okay, now after we input this image to the encoder, you might see the smile, the skin tone, okay, the color of the skin. Is gender, is male or female, with a beard, or did he wear glasses, or and the hair color, okay? Then we will give you some of the value. For CAE, this value will be fixed. And it will use this feature value, fixed feature value, input to the decoder. And hopefully, the decoder will output the image exactly the same as the input. But for VAE, no. Again, it will try to represent it, this feature, okay? The degree of smile, okay? The skin color, the gender, the beard, and so on. It goes like this. It's not a fixed value, okay? For example, you want to measure the degree of smile. For the boy here, he looks sad, so the value below is negative, okay? For Mona Lisa, the value could be 0 because you're not quite sure she's smiling or not, okay? 0, okay? And for the girl here, definitely the value should be positive. Now, anyway, for the boy here, the degree of smile will follow the distribution. It's a distribution, okay? Now, your encoder is trying to learn what? Learn the mean. Okay, the mean could be like this. And the standard deviation. For Mona Lisa, see that? The mean is 0, but the distribution is, the variance is wider than any others because you have so much about the uncertainty, okay? If she's smiling or not, okay? And for the guy here, just see that, if the value is very close to 1 and the variation is small, so we are pretty sure he's quite happy now, okay? So anyway, it's not a fixed value. That's the idea about variational autoencoder. All the encoder try to learn is the distribution, okay? By measuring the mean and standard deviation. That's it, okay? Let's learn from your encoder. And based on this distribution, you will input to the decoder. So every time when you apply VAE, the output won't be exactly the same. But the good thing about image generation is what? You can use the variation here to create a lot of samples. For example, for defect detection, you don't have enough defect sample. You can use a very limited number of defects, and you change the variation or change the mean a little bit, and you can create more images. That's why variation autoencoder is so popular nowadays, especially for image generation. Okay, so that's the idea. Okay, let's take a break.